Hello there, ATSEVS533 students. Dr. John Truggy, and I'm just here to welcome you to Module 2. We're getting ready to start talking about the physics of climate, especially stuff about radiation. We're trying to explain why the planet is the temperature that it is, so that when we can start understanding models for how the temperature is going to change and so on. Now, in order to get to this lecture, you've already had to look at that stuff that's about a 100 level understanding of physical climatology. And I'm very serious about the fact that I'm not planning on teaching all that stuff again, okay? To get into this class, you already have some prerequisites. You've already seen things like Stefan-Boltzmann's law, Wien's law, the basic terminology of what happens when radiation hits an object. Processes like absorption, emission, scattering, reflection. I'm not going to teach you that vocabulary again, okay? Now that doesn't mean that there aren't parts about that we are going to be teaching again, but the basic idea that matter emits radiation, and when the radiation is incident upon an object, that is to say it hits an object, there are certain things that can happen. It can be absorbed, it can be reflected, it can be transmitted, it can be scattered. That level of understanding you need to get from those videos if you haven't retained it from when you took the class originally. All right, so if we're really in the business here of trying to sort out why the temperature of the Earth is what it is, or maybe a better way to put it would be to say, why is it changing the way it's changing? We need to understand the physics of what it means for an object to be changing temperature. And at a very basic systematic type level, we can always describe a change in temperature of an object as being proportional to, that's what that little alpha symbol there means, proportional to. The change in temperature is proportional to a change in internal energy of the object. The actual energy of the molecules as they wiggle around or whatever. Okay? Regardless of what kind of object, from the Earth to the food that's in your oven or whatever, changes in temperature are about how the internal energy in the object is changing. Well, there's a certain amount of internal energy in every object, and at all times that object, nothing exists in a complete isolation. It is exchanging energy with its surroundings. So there is a certain amount of energy the object is giving off to its surroundings. That's the energy out of the object. And there is energy that it is getting from the surroundings. That's energy into the object. The difference between the amount of energy coming into the object and the energy going out of the object then is that change in internal energy. Therefore, changing the temperature of something, be that the planet, or be that the pizza in your oven, is all about the difference between the amount of energy going into the object from its surroundings and the amount of energy coming out of the object and going out into its surroundings. And probably the easiest example to think through as to how this is going to work is to think about a dish put into a refrigerator. I don't remember where I found this picture of a messy refrigerator, but let's say you got something in a pot here, and we've taken it out, we've served, and now we put this warm dish into the refrigerator. What is actually happening? Well, this object is warm. And all the radiation laws tell us that objects are emitting radiation, but by Stefan-Boltzmann's law, which tells us that the amount of radiation that the object is giving off depends on its temperature, we know that this dish is actually emitting a lot of radiation compared to those cold things that are around it. The salsa and whatever else is there, and the mayonnaise and whatever's all around it. So every square inch or every square centimeter or whatever of that dish is giving off radiation. In fact, giving off a lot of radiation. It's losing energy out to its surroundings. Now, all that stuff around it, the salsa, the mayonnaise, the cake, whatever's all in there, is also matter. It's also giving off radiation, but by Stefan-Boltzmann's law, we know it's not giving off all that much. So, because these objects around it are giving off less radiation, our hot pan or pot or whatever that is there is receiving less energy from its surroundings. It is having less energy coming in than the amount of energy that is going out. So energy in minus energy out is a negative number. That is, remember, from our basic understanding then, we are having a decrease in the amount of internal energy in that pot, and the change in temperature is proportional to that change in energy. So if the change of energy in that pot is negative, apparently the temperature trend is negative. The dish is going to be cooling. That's a whole lot of thermodynamics to be telling us. You mean I put a hot pot in the refrigerator and it started getting cooler? Yeah, okay, but that's what's going to happen, is it's going to start getting cooler. That is what the laws of thermodynamics and so on are telling us about this pot. Now, as the pot gets cooler, it's still emitting radiation, because it's made of matter. That's what matter does. But the amount of radiation it's emitting is decreasing. As its temperature falls, by Stefan Boltzmann's law, it is emitting less radiation, but it is probably still emitting more radiation than it is receiving from the salsa, the mayonnaise, the cake, whatever is all there in the oven, in there. So it will continue to be, in the refrigerator rather, so it will continue to be having a negative energy balance, and its temperature will continue to fall until eventually it reaches an equilibrium, a thermal equilibrium, where its new temperature is such that the amount of radiation it gives off at that temperature is equal to the amount of radiation it's receiving from its surroundings. The object is still emitting long-wave radiation, presumably long-wave. The objects around it are still emitting radiation, but it adds up to zero for the object. The amount of energy in is now equal to the amount of energy it is giving off, the amount of energy out, so its change in energy is zero, and since the change in temperature is proportional to the change in energy, if the change in energy is zero, there is no change in temperature. It doesn't mean the temperature is zero, it means that the change in temperature is now zero. We have reached a thermal equilibrium. This pot is now in thermal equilibrium with the surroundings around it in a refrigerator. That's what we're trying to figure out for the Earth. We are trying to figure out for the Earth how it's in or not in some kind of thermal equilibrium. There is energy that it is receiving, principally from the sun, and there is energy that the Earth atmosphere system is losing to space, primarily in the form of long-wave radiation being transferred out into space. We know from Module 1 that this is not in balance. Well, I'll take it back. We know from Module 1 that the change in temperature is a thing. The planet is apparently getting warmer. So, since change in temperature is proportional to change in internal energy, that means that there's a positive change of internal energy. The planet is physically getting more heat and more energy in it than it had before, which means the amount of energy being received is apparently greater than the amount of energy out. Somehow or other, this energy balance has been screwed up. Oh, well, in a class like an environmental science course about climate change, you know where this is going. But we got to figure out how it happens, okay? Before we do that, though, let's do a couple quick questions. Question 1. Changes in the temperature of an object are always proportional to A, the amount of radiation the object is emitting, B, changes in the internal energy of the object, or C, the amount of radiation the object is absorbing. What are changes in the temperature of the object proportional to? Make a choice from those three options and get a little feedback before you move on to question 2.